Hello again. Today, let me share. Today, we already talked about the exam logistics on May 5th. I told you about the assignments. Now we're going to continue the lecture from where we start last time about program execution time. The thing, we're still in chapter 2, okay? And we're going to finish chapter 2 today, inshallah. This has to keep happening. طيب. Program execution time. The HCS12 microcontroller timing reference is a clock called the E-clock. Sometimes they call it the bus clock. This E-clock is the time reference for all instructions. Yani, you say that this instruction will consume 2 E-clocks, 3 E-clocks, okay? What is the E-clock? The time of the E-clock.
دكتور مش مبين شيء، انت مشير شيء؟
والله صحيح. You don't see my screen?
No, you see.
شايفين
شايفين
دكتور. يس.
You see my slides?
يس.
موجودين.
يزيد.
انا الشاشه سوداء عندي.
عندك المشكلة يا يزيد. شو الشاشة؟
دكتور بقدر اطلع وارجع؟
I stopped sharing. I'm sharing back again. هيني I'll try to share again. شايف إشي يزيد؟
لا نفس
طيب يلا اطلع وارجع. يلا هيني بنستناك. Let's wait for Yazid, okay, guys. I'll pause the recording for a second عشان ما يكونش الفيديو long. Okay, Yazid is back and we're recording. Let me share again. Okay, so you see my slides, everybody. So in HCS12, there is something called a clock called the E-clock is the timing reference, which means timing reference, every instruction, مثلا load accumulator A with something. This مثلا consumes X E-clocks. Okay? You say, okay, push or pop executes or pull, it's here, pull, uses Y E-clocks, okay? Yani 2 or 3 or 4 or 5, whatever, E-clocks. So it is our reference. So to understand or to do the math, to compute how long will a program take to execute, you count how many E-clocks it consumes. Now the E-clock is sometimes called the bus clock. The time, so a clock is something like this, clock, square waveform. The time T here is what we're talking about, okay? From a rising edge to a rising edge. The time T clock equals, طيب, the frequency of this E clock equals, let me go to my board. This is too tight here. Okay, so we talk about an E clock. The frequency of the E clock, which is the reference for all instructions, equals half the frequency of the oscillator clock. What is the oscillator clock? It is this oscillator on the microcontroller.
8 mega or 16 mega.
Ah, yes, exactly. طيب, it is this piece I'm pointing. If you see my camera, I'm pointing at. طيب. Now this clock here is external that we have on our board. It's not part of the HCS12. It's part of the board that this manufacturer of the board put there and interfaced or provided the frequency to the microcontroller. طيب, how fast is this oscillator frequency? For us, we know how to get it, right? You can go to the manual. For us, let's do real math here. So if we go to our resources and check our Dragon board manual, the Dragon manual, the board manual, not the CPU manual, here you can find the frequency of our oscillator. That is, and I'm going to search for it real quick with this. I don't want to go searching. طيب Control F. Oscillator, clock, طيب megahertz. Okay. طيب, where is it, man? It is here. It is here, but let me. And I checked it the other day. It is 8 megahertz. Yes, here. The crystal. You see it? It has an 8 megahertz crystal. Okay. So the default bus speed is half this frequency, 4 megahertz. طبعا using PLL we can raise it. This is something we're going to talk about later. So the crystal, the oscillator, the crystal is the oscillator, okay? The crystal is the oscillator, is 8 megahertz, okay? So if the E clock, the oscillator is 8 megahertz, you divide it by 2, then your E clock equals 4 megahertz. Frequency of the E clock. This means the time, okay, the period of the E clock equals 1/4 megahertz, right? Equals 0.25 microseconds, right? So a push, for example, yani last time we did the delay, right? When we blink the LEDs, we did the delay. We used push-pull, right? So the push takes 2 E cycles. The pull takes 3 E cycles. Yani the push, if the oscillator clock was 8 megahertz, then the E clock frequency is 8/4 megahertz, right? Over 2, sorry, equals 4 megahertz. So time for the E cycle equals 0.25 microsecond. So this instruction will consume 0.25 microsecond times 2, right? Equals 0.5 microsecond. This will consume 3, right? 0.75 microsecond. And I'm sorry for my handwriting, and I hope you understand it's very bad because I'm writing on a screen vertical instead of in front of me, okay? I don't want to flip the laptop because I'm using it. But I hope you can understand my writing. Right. These instructions, push is 2 E cycles, 3 E cycles. A push, a pull, a push, a pull. Using this delay, we used it before. Why do we? Can we guess why we do here a push, a pull, a push, a pull?
To make a loop or
to not affect anything, yes, to waste time, right? When you push A is an instruction. We're gonna see it in the stack. Push A stores A in the stack. Pull A brings it back. Pull A in other microprocessors they call it they use the instruction pop instead of pull. Here we use pull. So pull A, you pull it out from the stack. Push, you store it in the stack, okay? So you're not really affecting A, you're not affecting the stack. So you push something in, stack is part of memory. You store something in memory, you read it back. You stored it and read it back. You stored it and read it back this many times. طيب. How many times here? 1. 2, 3, 4, 5, 6, 7. 7. Each push and pull takes 5. This is 35, right? 35. The no operation takes 1, right? 36, 37, with decrement and branch not equal, takes 3 e-cycles. So the total here is 40 e-cycles. طيب, how long will these take to execute? 40 e-cycles. And this is the math we did in our example last time. But so 40 e-cycles will take this much time to execute at 8 megahertz oscillator frequency أو crystal. قديش time? So what we do is, okay, the e-clock is 2 times, right? The oscillator frequency, the time doubles, صح? The frequency is half, the time doubles. 2 times 1/8 megahertz, right? Times how many clocks? 40. So هذه 0.25 في 40 يعني 10 microseconds, right? طيب, last time we did a delay of how much? The delay we did يعني هاي 10 microseconds. So the املأ الفراغ هون 10 microseconds. طيب, what do I do if I want to do 500 millisecond delay? I have to repeat this how many times?
50 times.
50,000 times. High micro.
Awesome.
Right? 50,000 times. So you put it in a loop, right? Loop 50,000 times. Execute all these stuff. Loop. Yani, this is one thing. You put it, you put a counter in X here. You initialize X with 50,000 times. Each time check it and go back, right? So you get your delay. And we saw it. We saw it. And we did this example. Okay, do we understand what is a program cycle? Yes, طلال.
لا يا احمد، كنت اسال هسه الكريستال 8 ميجا والاربعه النص بتكون الباس كلوك.
باس كلوك الاي كلوك.
خلص تمام.
يعني نصها. Frequency is the half, so the time to execute is double, right?
تمام.
Times 2.
دكتور، ما عندنا better ما عندنا better way to delay.
We have interrupts. We have real-time interrupts. We're going to cover it in chapter 6, inshallah. Yes. Yeah, طبعا this is a waste of time. You shouldn't use it. Yeah, we have something called real-time interrupts. We're going to use them. Yeah. And timers and another timers. Okay. So this is delay-based loops, okay? Wasting time. Example for 100 milliseconds, example for 10 seconds. So, well, when you load your counter here, example X is a 16-bit number, right? And you just keep this in mind. So a 16-bit number, the maximum number you can store in it is what? 65,536? Well, 3,500.
Yes, 6.
Okay, يعني something close. اللي هي 64K. يعني. Okay. So this is the man. يعني you cannot put in X 70,000. You cannot. It will not hold it. The biggest number is 65,500 something. Okay. So in this case, if you need to repeat something 70,000 times, 80,000 times, 100,000 times, you can call this loop that executes 50,000 times. The maximum here is 60,000. You call it مثلا. Here he did it 20,000 times and called it 100 times. So he's doing this delay how much? 20 times 100 يعني 2 million times. صح? 2 million times. So you do an inner loop and an outer loop. Okay. Is this clear? Any questions? I'm finishing chapter 2. Let me know if you have any questions. Yazid, all good? Yazid. Ahmed, مو مني رافع ايدك؟
لا كنت لما سألت عن
okay,
الكريستال.
اوكي.
ترك مجال سؤال.
يس محمد.
في الديلي الاول اللي كنت حاطه قبل ما تعمل انر لوب او اوت لوب بالضبط، لا اللي قبل هذا برضه كمان بالضبط. هنا كيف عرفت انه 40 سايكل؟ انا عديت طلعوا 20 سايكل باللوب.
هذول؟
اها
البوش is 2, البول is 3, right?
تمام.
So 5. يعني البوش after it a pull هاي 5 وهاي another 5 10 15 20
تمام
25.
انا حسبتهم غلط. خلص
اوكي.
تمام.
30 35 وهذول 37 و 3 40. طيب
مزبوط.
how did we get the 2 and 3? Did I show you how before? Do you want me to show you how? ولا did we see?
From the manual of data sheet, yes.
From the manual, you know where to look at?
في
You count the
digits
number of
عند
letters.
Yes.
Let me show you real quick. So you go open the instructions. So with the push, Control F, push A, صح? Push A. Where push A? Push A. Push A. You come. We're at HCS12. See these letters? O, S, 2. So it takes 2 E cycles. The pull A. Oops. Down. Pull A 3 1. See the U F O 1 2 3. So 3 cycles. From here we get it. In nope was one E cycle and OP. The nope operation. No operation يعني. Where is it? Here it is. 1 E cycle here. Okay. Okay guys.
دكتور.
Yes, Mariana.
هذول الرموز لإيش بيمثلوا الأو؟
Okay, these symbols, if you go before, it means what is the cycle. So we're talking about a cycle, but what is the cycle? Is it a write to memory? Is it a read to memory? Is it, is it, yes, is it a CPU cycle? So it is at the beginning here. It tells you, مثلا F, I remember, is a free cycle. Free cycle, and you're not using the bus. Okay. So I think at the beginning you can figure them out here. Each of one, but each letter takes the same time. Okay, but what is the CPU busy doing at that point of time? Is it using the bus? Is it not using the bus? Is it writing to memory the higher byte or the lower byte? You know, that's the thing. Introduction, program model, mass, data types, or organization. No. It is somewhere here, but بصراحة I usually when I want to check them, it is faster. I find them faster here in this manual, in the instruction set here. HCS12 instruction set. They are here. They are here. These are the addressing modes. These are the machine coding for the machine instruction. And here you are. See, access details. So F is a free cycle. CPU doesn't use the bus. Small g read the P page internally. The big O optional program for word fetch P. If بعدين small or capital letter مثلا S small 8-bit stack right, S capital 16-bit stack right. Okay, يعني every letter means something what you're doing, but it is gonna take يعني 1 E cycle. Every letter takes 1 E cycle. Okay. All good? We're done with chapter 2. We're done with chapter 2. As I said, chapter 3 is about using Code Warrior. Chapter 4 is about revision of C programming. Chapter 3, like 5 is C programming. Chapter 4 is what we're going to start right now. Is advanced assembly programming. And again, here, expect me to move fast. Slow me down if you think you need to, okay? It's, yani, you'll figure out that most of the things we did in class already. A lot of things we already did. So it's not gonna be a big headache. Time is 4:06, okay. And we still have, okay, good. So in this chapter, we're going to talk about subroutines, although we already wrote a subroutine, right? In that blinking program, in the flipped classroom, when we did blinking, the 7-segment display, we did delay loops, just like what we did, and computed the time, but we didn't repeat it again and again, right? We wrote it once, we branched to the subroutine, and we came back. It's like calling a function in C. So we're going to talk about subroutines, how to call, how to return, how the stack is used by these subroutines. But before that, we need to understand what is the stack, okay? Then the second part of the chapter, we're going to be talking about interfacing, okay? Interfacing with through I/O pins. طيب, as we all know, our program, and when we wrote our program, we used to go to design our program, right? Either by through designing a flow chart or model based, and you had a plan for what you want to do. I want to bring this, add it, then increment a timer, a counter, check if we reached our goal, then do this, you know, an algorithm. So a program is typically an algorithm that is supported with a data structure. Okay. One of the very important data structures, and famous data structures, for those who come from the computer engineering background, have studied a full course about data structures. They learn about queues, about stacks, about arrays, about strings, about linked lists, about a lot of things. However, at this point of time, this kind of class, arrays, we know them, and we're going to use them in C, and strings. In this particular chapter and lecture, we're going to talk about a stack. A stack is something that uses the last in, first out structure, which means, as opposed a stack, imagine you have 100 dishes, and you were asked to clean these dishes and put them on the side. So you put the first dish, then you put the second dish, then you put the third dish, then you put fourth, fifth, right? So you make a stack of dishes, right? If somebody asks you to give him a dish, you cannot go slip one from the middle, right? Just like they do in Tom and Jerry, or from the bottom. You take the one on the top of stack, top of stack, right? So you bring the one on the top. So dish, the green dish, you bring it over. Then it is clear for this red dish to bring it over. Then it's clear for the blue one to take it over. So whatever you put first is the last one you take, right? So first in is last out. The first thing you put is the last one you get, right? You access. Opposed to something called queues. Queue, زي الطابور, the first in comes keeps moving. Every time you bring something in here, this takes a step forward, this takes a step forward, and so on. The first one that goes out of the queue is the first one that came in. So we call this a FIFO, first in, first out, okay? While in the stack, they call it a LIFO, last in, first out. Okay, this is a data structure. You can implement it in your program for any kind of application. Now here, we're going to talk about not a data structure stack that you build in your program. We're going to talk about a hardware stack that is already built for us. It is there, okay? And we can just use it. It's part of our memory. So the stack concept, we have this memory range, right? And if you remember, when we wrote our program, let me go open one of our programs that we wrote. Remind you what we did. Where are the demos? Class demo 3, for example, here. Let me just go open this program. I don't want to open the whole project. I'll just edit this file and see the text. So remember this program we wrote to convert to BCD and ASCII, a program we wrote. The data definitions were here, right? The program itself started at the flash memory, the RAM start here, right? And our entry, the program counter, what comes here when we first turn on our computer or microcontroller, the program counter will come point to this instruction. What is this instruction? This is the first instruction. Okay. How does the program come here? How does it know it comes here? It knows by the reset vector. There's a reset vector at an address in memory that is checked for. The program counter will go take the address where the program will start at. We're going to cover this in resets and interrupts. So the first thing we did here when we started our program, the application code started here, right? Convert to BCD, divide by 10, take the remainder, right? Store it in a memory location, then add 30 hex to convert to ASCII, and so on. Then blink the LEDs, right? What was here? And here was we did the delay, 500 millisecond delay, turn on the LED delay, turn off the LED delay. How do we call the delay? Branch to subroutine. The subroutine is called delay here, and it contains this code that we just saw, and we learned how to compute the time. Okay, and at the end, there is an instruction return from subroutine. I'm pointing to them because I'm gonna talk about them shortly. Return from subroutine returns you back to the instruction right after the one that called the subroutine. Anyways, what I want to talk about here is the stack. So the first instruction we did here, initialize the stack pointer. We loaded S. S is the stack pointer register with the last memory address in the RAM plus 1. طيب, what does this mean? So this is memory. And we know that RAM starts at address 1000, right? This is RAM start, right? RAM start. And RAM end, what was the RAM end? 3FFF, right? And we know how. You can, if you open it in Code Warrior, right click here and you go figure it out, right? The last memory location was this location, for example, which is $3FFF, right? طيب. What we did, we loaded the stack pointer with what? 3FFFF plus 1, يعني قديش? With immediately
4000.
4000. So the stack pointer register equals 4000, which means it's going to point to this instruction, to this memory location here, which is out of the RAM. The RAM is here. The RAM is here. 4000 is the beginning of what? Program memory, the flash memory, the RAM, program memory. Okay, but we're not going to store here. What we made it point to a one location lower than where we want to do the stack. So here in the program, we're going to use the RAM. We start from 1000 and we're going to use as much as we want. And for the stack, we're going to use the last parts, or the last the location at the end of the addressing of the address space of the stack. So you make it point to the location right after the RAM. So when you go do a push A, what does push A do? If you go to the manual, and I'm going systematically here for you guys to, we're not going to cover all instructions, so you're going to be using the manual. So push A, what does push A do? This explains what push A does. You see my mouse, right? First thing that what happens is the stack pointer is decremented by 1 and stored in the stack pointer. You decrement stack pointer by 1. Then you take A and store it in the memory location where stack pointer is pointing at. So, after this, what happens? Stack pointer will become what? 3F, right? Then register A is gonna be stored in memory location address 3F. Okay, so stack pointer is gonna decrement by 1 and go point here. Okay, then the push will save A here. A طبعا A could be مثلا any number 1, 2. A is an 8-bit register, so you store an 8-bit number 1, 2 in the memory location. طيب, what if I did a push X and X was $3456? Let's check it. So Control F, push X here. Push X decrements the stack pointer by 2 because X needs 2 memory locations to store it at. Then X is stored according to the big Indian convention. So the higher part of X will be stored in the where the stack pointer is pointing at. Higher part is stored at lower memory location. Lower part is stored at higher memory location. Okay, so what happens here? Stack pointer decrements by 2, so 2. So it will point to, this is 3FFE, and this is 3FFD, right? So stack pointer after this instruction, stack pointer will become stack pointer minus 2, يعني what? 3FFD here. We booked now, now we booked 2 memory locations, this one and this one, and we want to store 16-bit in it. So X high goes here, X low goes here. طيب. Well, so in terms of numbers, 3, 4, and 5, 6. طيب. And so on. So a push, the push affects, does 2 things. It first changes the value of the stack pointer by decrementing it with a 1 or 2, depending on the size of the thing you're pushing. If 8-bit, you decrement stack pointer by 1. If 16-bit, you decrement it by 2. By decrementing the stack pointer, you're making it point to a new type of stack that is empty, that you can store something in. Then you move to memory this thing that you're pushing, you move it to the locations you want. طيب. How do I read it back? I use the pull instructions. Okay, so assume we have this example. This is the stack, regardless where we initialized it. Well, you know what? Let's use numbers. ما في مشكلة. Let's assume this address is address 2000. Any problem? No problem. Okay. So, and we had these instructions. We have a few registers that you are already initialized. مثلا A equals 1, 2, B equals 0, 0, X equals F, F, E, E, بكفي. And we did this program. We did push, well, مش هيك, push PSHX, push X, and then we did push A, push B, pull A, pull X, pull B. What is the value of X, A, B, and stack pointer? This is a typical exam question, huh? After executing these instructions. Well, the push X does this. Push X will affect the stack pointer by decrementing by 2, right? 1, 2. So it's going to point here. So 2000 minus 2 is going to be what? 1 F F E. صح؟ هذه تكون 1 F F F 2000 هاي 1 F F E. So here the stack pointer equals 1 F F E. Will memory location so we booked these two memory locations. هذا we didn't know what's here. Now we booked two memory locations. We're going to put X here in these two memory locations as follows: F F E E. Then push A is gonna cause the stack pointer to decrement by 1, right? So it will become 1 F F D here, 1 F F D, point here, and store A here. A is what? 12. 1, 2. Then push B, stack pointer here is going to become 1 F F C. طيب. And you're going to store B, which is 0, 0. Then pull A. Pull A, we just checked it in the manual. I don't want to keep jumping. First, it reads the memory, then it increments the counter. Okay? So A here will get what's in the top of the stack. What's the top stack? This is the top stack, where the stack pointer was pointing at 1 FFC. A takes 8-bit, so the 0, 0 will go to A. So A will take the 0, 0 here. And then the stack pointer, now this is empty, you can consider it empty. The stack pointer increments to point to the new top of stack. Okay? Stack pointer becomes stack pointer plus 1, يعني قديش؟ $1 FFD. Then we pull X, then X will take 16-bit that the stack pointer is pointing at, اللي هم هذول 16-bit. So $12FF. Then the stack pointer will decrement by 2 to point to the new top of stack. So it will go here to the 1FFF, $. Then pull B will take to be what's the stack pointer is pointing at, 1FFF, EE, $EE, and the stack pointer will decrement and go back here to 2000. So at the end of the program, our stack pointer value is 2000. Sorry, Stack pointer value is 2000. Okay. X, the last value for X is 12FF. The last value of B was EE. The last value of A was 00.
دكتور ممكن سؤال؟
Yes. So these were the initial values. These were the values at the end. And we did the step by step. Yes, تيمة تفضلي.
الدكتور بيقول إيه على أول شيء باخد ال00 بعدين بيعمل increment للstack pointer.
You're talking about the pull here?
pull إيه.
So
بالضبط.
pull. Yes, good question. يعني pull, when you pull something, you have to take where the pointer is pointing at, then you change the value of the pointer. If you change it before, you lose. Yani thank you for raising this. Yani this is the main purpose behind the stack. You don't need to worry about the addresses you use to store your stuff at. You only care about the order, what's in the top, what comes after it, what is before it when you write your code. You care about what's on the top of the stack. You don't care a lot what was the address of that memory location. Can we directly go and read this memory location? We can, using load accumulator A, this address. But why should I have to remember all these addresses? Okay, you can just use the stack to not worry about the addresses. Okay, a push decrements the stack pointer first to reserve empty locations, then you move data to store it in that memory location. The pull, you read memory. You need memory from a memory location, you have to have a pointer. The pointer is a stack pointer, so you read first, then you adjust the stack pointer to point to the new top stack. If you do if you change the stack pointer value first, you lose the data. Okay?
Thank you.
Welcome. Okay, guys, so this is the concept of the stack. Here are the stack instructions: push A, push B, push C, CCR code register. طبعا this is equivalent for STA. You can use for push A. This is an equivalent for store accumulator A, 1 comma stack pointer pre-decrement by 1. Right? So what does a stack store accumulator A 1 comma minus SP? It means decrement the stack pointer. Okay, stack pointer equals stack pointer minus 1. Then store accumulator A at the memory location where the stack pointer is pointing at. Okay, so equivalent instructions we know. So the push and pull. I think we're almost done. Some examples, look at them. I think we did examples almost the same. Okay, next time we'll start with subroutines. Subroutines use the stack. Any questions, guys? Okay, if you have any questions, time is over and I don't want to hold those guys who have another class. I'm gonna stop here. You can stay for questions if you have. Thank you very much and see you Monday at 3:30. كل عام وانتم بخير.